Welcome you all to this course on electron diffraction and imaging. In today's class, we will discuss about how to find out distance between different planes, interplanar spacing, how to determine. Similarly, interplanar angles, how to determine, we will discuss it. Okay. How we can go about is normally what we do is that this can be done in real space as well as in reciprocal lattice space. Okay. We have already learned about the relationship between the vectors in real space and the vectors in reciprocal space. Okay. Suppose we wanted to find out angle between interplanar distance in using the real space concept itself. We do not want to invoke the reciprocal lattice vector at all. Then what we have to do essentially is we should know two vectors which are lying in a plane. So, suppose HKL is the indices, Miller indices of a particular plane. If you know two vectors, okay, R1 which is V1 W1, this is how we can represent it, R2 which is U2 V2 W2. Okay. If these two vectors are lying in a plane, what we should find out first, okay, is essentially the vector which is normal to this plane. Okay. These two vectors are there. We find out the cross product of these two vectors. Okay. That vector is perpendicular to it. Find out the for that vector what is the unit vector in that direction. Okay. Then find out the interplanar distance magnitude. Then in the vector notation we can represent it. So, that will essentially turn out to be, okay, suppose I wanted to find out DHKL R1 cross R2, okay, divided by R1 cross R2 magnitude the whole squared into V, the volume of the unit cell. Okay. Essentially, in fact, this is nothing but equal to R1 cross R2 by modulus of R1 cross R2. This gives the unit vector in this direction, interplanar direction, and V is the volume divided by R1 cross R2 is that area of the unit cell. So, that will give the distance equivalent, because this is essentially a scalar quantity. This is how this expression is being used. So, we have to use this expression. But what is essentially important is that in this case we should know what the volume which is going to be. Okay. But generally the lattices could be essentially simple lattices. We know how to find out the volume. If it is a triclinic lattice is there, how do we find out the volume? That is the most general case which we can consider it. So, we will come to how to determine this volume. Okay. The other way in which these distances could be measured is using the concept of reciprocal lattice. So, the plane HKL, okay, is nothing but indices of the vector in the reciprocal space. So, there any vector, if I take it d star HKL, this will be equal to, okay, H into A star plus K into B star plus L into C star, correct. We can write it this way, and we know DHKL star dot product of this, if I take DHKL, okay, this is nothing but equal to DHKL star, the mod squared it will turn out to be, okay, and this will be nothing but H squared, okay, A star squared plus K squared B star squared plus L squared C star squared plus twice HKL into A star star B star plus twice K into L into B star dot C star plus twice H into L into A star dot C star, correct. This is how essentially it will turn out to be, okay. And we know that once we have this magnitude, okay, DHKL, the magnitude is essentially is going to turn out to be 1 by DHKL star, correct, squared, this will be that whole square. So, using this relationship you can find out. Here again if we take A star dot B star, then it will be equal to, for example, equals modulus of A star into modulus of B star into this will be cos angle between A and B will turn out to be gamma, correct. So, essentially what we require is this sort of, not gamma, this is gamma star angle between these two vectors, okay. That is essentially if we represent A star B star in terms of a coordinate system, in this direction A star B star and in this direction C star, okay. This is the angle gamma star between them. This will be alpha star angle, this will be beta star angle. Right. This way we can utilize it to find out. Okay. Now again that we know the relationship between A star in real space and reciprocal space essentially is A star will be equal to B cross C by A dot B cross C, which we write it as B cross C by V. Similarly, we can write it for others also. Okay, this expression can be used to find out. Crux essentially is that what is the relationship between these angles? This is how we have defined it in reciprocal space. Similarly, in real space also we can choose a coordinate system in which we define the unit cell. So, in that if this is A and this B and this direction it turns out to be C and this angle is gamma, this angle is alpha, this angle will be beta. Okay. To use this formula, essentially what we should know is what is the relationship between alpha star, beta star, gamma star in terms of alpha, beta, gamma. That information will be required, because what we generally have with respect to crystal structure is only in a real space which we have. Similarly, what is going to be the general formula for the volume in terms of A, B, C, the coefficients, okay, and also in terms of in terms of the lattice parameters A, B, C of the general unit cell which we have considered and the angle between these various lattice parameters, okay, in different directions, translation vectors in different directions. This is the information which is necessary to use this. So, the question essentially is how are we going to determine this. So, we know that any vector, okay, in a vector algebra, what we do it is we choose a coordinate system which is essentially a orthogonal system, correct, where the angle between all these are going to be essentially 90 degree, correct. This is a sort of a coordinate system which we choose it. Okay. In this system, anyway, since we will be putting other angles, I will just, okay. We can consider, okay, any vector in this system, if we consider as a vector which is lying like this, okay, we define this vector as A. How do we find out the magnitude of the vectors? Essentially, suppose this is x, y and z, then what is going to be, that is this vector A can be written as I into A1 plus j into A2 plus k into A3. This way we can write it. This can also be written as, instead of A1, A2, A3, essentially represent the components in x, y and z. So, sometimes it is written as I into Ax plus j into Ay plus k into Az. This is the way also we write this expression, correct. The other way in which we can do it is that what is going to be the projection, the angle which it is going to make with respect to this, okay, and find out what is going to be the magnitude, okay, of A. So, then we can write A can be written as I into, okay, modulus of A into, I will write this angle which it makes as cos alpha A. This is the angle which it makes, this is alpha A, okay. With respect to y axis, I into modulus of A into cos beta A j plus k into modulus of A into cos beta cos gamma A. This way also we can represent it. There are many ways in which these vectors could be represented. So, in this representation, essentially this magnitude is a scalar quantity, okay, and then with respect to the angle which that vector makes with respect to a various axis, this form in which we can write it, okay. So, now we will come back to the problem of finding out the volume cell. Now, let us consider x, y and z. Suppose I consider a vector A in this direction, vector B in this direction. Just I am taking as a specific case, it could be a general one. I am taking it so that it becomes a little bit simpler to solve it, okay. And a vector C, okay. These are all the translational vector in these directions. If we take this, with these vectors, we could now construct a unit cell, correct. So, what essentially will happen is that, suppose I take this like this, okay. So, this is essentially how the unit cell is. No. Yeah. A, okay. What is essentially will happen is, this way it will come like this, okay, from here to here, here to here and here to here. This is how the unit cell will be, correct. Now, this is essentially what it is going to be, A, B, and this is going to be the C vector. This we assume it to be a triclinic lattice. Okay. Now these vectors A, B and C can be in written in terms of each one of them in terms of vector coordinates, that is orthonormal system which we have chosen. Okay. Then we will be writing an expression like this for A vector. Similarly, we can write an expression like this for B, I into B into cos alpha B cos beta B plus k into modulus of B cos gamma B, right, this way. And this modulus of A, B, C is essentially the translation vector in this, the magnitude which we can assume it to be A, B and C. If we take in this form, okay, now what essentially is that this itself can be written as A, B, C can be written in forms of A cos alpha A cos beta A cos gamma A, B cos alpha B, B cos beta B and B cos C cos alpha C, C cos beta C, C cos gamma C, okay, into I, J and K. This sort of a matrix notation which we can write, correct? The sort of coordinate system which we have chosen, okay, A is matching with this. So, what is the angle which it makes with respect to this one? It is 0. So, that will cos alpha A will turn out to be 1, correct? Then the other two, cos beta A and the cos gamma A is going to be 0, okay, because 90-degree angle makes. Okay. So, this expression will turn out to be A 0 0. Then similarly here it will be, I will just write that expression, but you can work out all these aspects. Cos alpha beta B cos for B, cos beta B 0, C into cos alpha C, C cos beta C to C cos gamma C, okay, then into I j k. So, this is the expression for A, B, C in terms of the orthonormal system of coordinate system with which we have. And angle between these will be turn out to be gamma, angle between these two axes will be going to be alpha, this angle is going to be beta. These are all the angles with respect to a unit cell which we have, but now we have measured all the angles with respect to the coordinate system with which each of these lattice vector translational vectors of the unit cell is defined, correct? Now, we know that A dot B will be equal to modulus of A into modulus of B into cos gamma, correct. Similarly, B dot C equals modulus of B into modulus of C into cos alpha, then C dot A modulus of C into modulus of A into cos beta. We know this expression. This is one expression which we have. From this equation, here it is A, B, C, we can find out the value of A, B and C. Then also we can substitute on this side and find out, correct. So, if we try to do that, then you know what will happen. A dot B, if we try to do it, what is A here is equal to I into A, correct. What is B? Equals I into B into cos alpha B plus J into B into cos beta B, correct. If we take A dot B, what is it which is going to turn out to be? This will turn out to be A into B, okay. A dot B equals to B cos alpha beta, cos alpha B it will turn out to be, correct. Because that other one, that J, because I dot I only will be equal to I dot J equals 0. So, now we have this expression. This can be equal to, okay, modulus of A into modulus of B into cos gamma. This modulus is AB. Now, we get that expression, right. Cos gamma equals cos alpha B, correct. So, now alpha B, we have got it in this matrix in terms of the angle between the two vectors, two lattice translation, the unit cell, we have got that information. Essentially what we have to do it is that information like this for all other angles. If we get it, now we will have an expression which is connecting A, B, C in terms of the modulus of A, B, C and the angle between them. That is all this whole game is. Once that information is available, we have. Okay. Similarly, if we do it, I will not go into work out all these details. I will just write the expression which one can work out for oneself. Okay. If we take this expression, that B dot C, okay, this will turn out to be BC cos alpha B cos alpha C, okay, plus BC, this what it will turn out to be beta B plus cos beta B to cos beta C, okay. This equals BC cos alpha, from which we will be getting a relation that cos alpha equals, okay, cos alpha B cos alpha C plus cos beta B into cos beta C. This is the sort of an expression which we will be deriving. Okay. But if you look here, beta B is what it makes with respect to this one, correct? This beta B will turn out to be 90 minus gamma. Okay. If we use that expression, then cos beta b will turn out to be sin gamma. Okay. We can substitute like this. Okay. Finally, I will just write down the final expression like that. It is essentially a working out an algebra. I told what the methodology which has to be used. It is essentially using this relation, okay, and in which we had already got this is BC into cos alpha, this is CA into cos gamma, and C dot A we have to take the substitute, then we will have that relationship. Finally, what it will turn out to be, A B C zero, B cos gamma, B sin gamma, this is 0, okay. This is C cos beta, C cos alpha minus cos beta cos gamma by sin gamma plus no. Here it will be CV by ABC sin gamma. Okay. I j k, and what is V here? This V is nothing but the volume of the unit cell. Okay. And this we know that in the expression which we have written, this cos squared plus cos squared beta A plus cos squared gamma A, this should be equal to 1, right. Similar expression holds for all of them. So, then if we write this term will turn out to be, for the last one, cos squared beta plus cos alpha minus cos beta cos gamma by sin gamma, okay, the whole square, plus v squared by a squared b squared c squared sin squared gamma. This will turn out to be 1. Okay. If we try to solve this equation, okay, what we will get as a final answer is, because here V is one term, a squared b squared is there, then all others are angle between the different translation vectors, different vectors of the unit cell. Okay. So, essentially now V squared will turn out to be a squared b squared c squared, okay, into 1 minus cos squared alpha minus cos squared beta minus cos squared gamma, okay, plus 2 cos alpha cos beta cos gamma. Okay. So, from this we will find that V equals ABC into root of this term 1 minus cos squared alpha minus cos squared beta okay. This is essentially is how the volume of a triclinic structure where there no symmetry is associated with it, none of the angles are 90 degree, we can relate them to the angle between that unit cell vectors and the lattice parameters. Okay. This is the general formula. So, once we have this formula, okay, then it becomes now very easy, okay, to find out if we are using a real lattice vectors like the way we have written here, it is going to be that D equals that is DHKL will be equal to if two vectors R1 cross R2, okay, which are lying in this plane divided by R1 cross R2 the whole squared into V we have, and R1 and R2 are defined in terms of ABC. Substituting this we can get this expression. Okay. Then once we have that is DHKL dot DHKL will be equal to modulus of DHKL the whole square, and from which we are able to find out and general expression. Okay. That is what it can be done. Or as I mentioned, the reciprocal lattice vector also, that concept if we use it, then DHKL the whole squared equals 1 by DHKL star the whole squared. Okay. This expression also we have written it. In this expression what we know that A star, B star and C star, we know the relationship. In that relationship essentially what we require is that A star will be equal to B cross C by V, that we have this expression which is there. Okay. This will generally turn out to be what is B cross C? B cross C will be modulus of B into modulus of C into sin alpha divided by V. So, now this is BC sin alpha divided by volume we know. So, now we get all the information A star. So, we can use this and then an algebra which we have to work out. Okay. That way we can get information about, okay, the interplanar spacing. We can get a general expression which one can derive. Okay. But if we use the reciprocal lattice vectors, we have to get another relationship, and that relationship is nothing but what is the relation between the angle alpha star, beta star and gamma star in terms of alpha, beta and gamma. We have to get that relationship, correct? That is a must, without which we can't do that. That relationship also I will just write it down, but as an exercise one can work out. Okay. That relationship essentially is cos gamma minus cos alpha by sin beta sin gamma. Similarly, cos star equals cos alpha cos gamma minus cos beta by sin alpha sin gamma. Cos gamma star equals cos alpha cos beta minus cos gamma divided by sin alpha sin beta. So, this gives the relationship, okay, of alpha star, beta star, gamma star in terms of alpha and beta in real space unit cell. Okay. Similarly, this expression, okay, gives A star, B star and C star in terms of A, B, C and the angles alpha, beta and gamma in real space system. Okay. And now the expression which we have written for D star HKL, I will just write down that expression again. Okay. Whole squared equals h squared A star squared plus L squared C star squared plus 2hk into A star mod into B star cos gamma star plus 2 k into L into B star C star alpha star plus 2 h into L into A star into C star cos beta star. Okay. This equals 1 by mod DHKL the whole square, correct? So, in this expression now we know A star, B star and C star in terms of it, and we have angle between alpha, beta and gamma star in terms of alpha, beta and gamma we have. So, using this expression now one can, okay, this is the most general expression to find out interplanar spacing for any crystal structure where there is no symmetry is involved. Okay. And using that symmetry, how the angles alpha, beta and gamma, we know how it is being defined. Like for example, if it is a cubic system, we know A equals B equals C and alpha equals beta equals gamma equals 90 degree. Okay. Using these expressions, substituting in it, we can get that value and find out an expression. Similarly, if it is a monoclinic structure, then we know A equals B not equal to C, alpha equals beta not equal to gamma, okay, and gamma equals 90 degree, correct. So, now we know how these expressions, using this we can derive from these expressions for the despacing, formula for despacing for various crystal structures. This I am not going to do that because I had already given a very general formula which has to be used and how to derive that, and using this formula one can find out expressions for the interplanar distance for various crystal structures. Why we require these formulas is that quite often when we wanted to find out or when we wanted to index diffraction patterns, we should be able to find out what the interplanar spacing is, because we use the Bragg condition, okay, which is nothing but 2D, 2DHKL sin theta equals n lambda, okay, to define the diffraction condition, diffraction peaks, correct. So, from this, that information which we can get, the information which we get, it is for a particular value of lambda which we use. What is the value of theta which we get it, from which the information experimentally what we get it is only the DHKL information. Okay. So, these formulas will be that's 1 by DHKL information what we get it in reciprocal space, from which we can get this information. Okay. This way one can derive formula for various structures. Similarly, interplanar angles also, when we have to find out, okay, how can we go about? Okay. Okay. That is, if we know cos theta is that angle, that is essentially what we do is, if two vectors which we define, okay, d star h1 k1 l1, okay, another vector is d star h2 k L2, or we can define two reciprocal lattice planes. Okay, let us consider the case two reciprocal planes, one with Miller indices H1 K1 L1, another with Miller indices H2 K2 L2. Okay. If you wanted to mathematically derive an expression for the angle between these planes, so what we normally do it is find out what is the plane normal corresponding to this, okay, for which you should know two vectors in that plane. Okay. Find out, once we know these two vectors, you know, and then find out the plane normal for each of these plane. Okay. The angle between the plane normal is what it is going to be defined, correct. For a cubic system, plane normal, it is easier to do it, but not for other systems. Other way we can consider it is that if you take a reciprocal lattice vector is in the same direction as the interplanar vector plane normals. Only difference between plane normal is in real space, okay, and reciprocal lattice vector is in reciprocal space, but each of these vectors are parallel to each other. Only difference is that the coefficients, when we consider, it is inverse of the other, that is the only difference. So, since the directions are the same direction they are, angle between two reciprocal lattice vectors, if we take it, that also we can find out. How do we find out the angle between two reciprocal lattice vectors? Suppose if one reciprocal lattice vector is there, d star h1 k1 l1, okay, another, the dot product if we take it, d2 k2 l2, okay, this dot product will be nothing but equal to modulus of, I will just for a simplicity's sake I will write it d1 star, okay, into this is d2 star, okay. Angle between them we write it to be cos theta, okay. This we know. So, how we can find out this values cos theta? Cos theta is nothing but d1 star dot d2 star divided by modulus of d1, correct, into modulus of d2, correct. Using this expression we can derive, okay, the angle between the different planes. Now we know d1 star, d2 star. Already how to get that information we have worked out for a general case. Then one can derive a formula for angle between planes for two vectors in reciprocal space. Okay. That can be used to get information about that. This what I will do is I can give you some exercise which one can work it out. So, that is the best way in which, because once you people derive it, this will be permanently etched in your memory and you will not forget it. So, only a general formalism which has to be followed with whatever is the necessary algebra, that is what I have discussed in this class. Okay. I will stop here now.